Hello everyone, I am Yiaoli, and today I'm presenting with Leshi. We're going to make a presentation titled Modeling of the Spatial Poisson Process by Programming. So let's start. First of all, what is spatial process? To put it in layman's words, it is a pattern consisting of points randomly located on the plane. A concrete example is dropping plastic balls on the table. If the balls are dropped randomly with an equal chance of landing in any place on the table, and their landing places are not affected by previously dropped balls, then it is said that the pattern of the balls on the table follows a spatial Poisson process. That is also why it's called the completely random process. On the right-hand side, there's a sample graph depicting the spatial Poisson process. In its mathematical expression, B represents the area of a subquadrat as the one shown in the graph, and lambda represents the point's intensity. Overall, P of x represents the probability that a quadrat with area B will contain x points. This equation is also called the Poisson probability function. So what are some applications of this spatial Poisson process? According to our research before our work, the spatial Poisson process is mainly used in the following ways. The list can go on, but it's worth pointing out that the common usage of this process in all of these studies is that it acts as a benchmark process. What does that mean? Recall the t-test or z-test in hypothesis testing. We assume our null hypothesis and calculate the statistic and compare it to the critical value. Then conclude whether or not our null hypothesis is rejected. So here it is the same. Our null hypothesis is usually that some unknown process is spatial Poisson, and then we calculate a statistic called Ripley's K. Then we reject or fail to reject the hypothesis to decide whether or not the process is completely random. However, we think that the spatial Poisson process can do much more. So we decided to combine it with an agent-based simulating software called COBWEB. It is a brainchild of Dr. Brad Bass, our supervisor, and it can be used to construct systems in which you can observe the interactions between different components in the system. In other words, it is a software that simulates the complex system. Now we will quickly present our results. The first pattern we realized is the default spatial Poisson process, the random pattern. A particularly useful feature we added is spatial heterogeneity, which means on the same plane, the user may set the process to have different intensities at different parts. The model also successfully passed a robustness test. It maintained a stable performance under small disturbances. So the spatial Poisson process is our start point of building more rigorous models. Next, Leshi will introduce dispersed and clustered patterns which are built on the spatial Poisson process but have more application value.
Hi, thanks, Lady. And I'm gonna introduce you the cluster pattern and the dispersed pattern. So for a cluster pattern, statistically, it is a task to group a set of objects in such a way that objects in the same group are more likely to be similar. But we would like to introduce the geometrical cluster, which is an incident rate that some variables are expected to happen in a certain range. So we take the incident rate and the range of diffusion as two parameters in our settings for cluster pattern model. Yeah, and for our two examples, we compare the two models with different diffusion rates, which is 0.3 on the left and 0.1 on the right, and it shows that the models on the left is more clustered than the other one. Yeah, and then we're moving to the dispersed pattern, and by Taylor in 1977, it is a process of assigning county seats to a group of counties of equal size. So specifically, it has two processes. First, it assigns the county seats to each counties randomly, following a spatial Poisson process, and it also adds in a modification that each county cannot have more than one county seat. So we also interpret this using two different comparison models, and the left one is more this it have more counties, and the right one has less counties. Okay, and that's the two patterns.
Okay, so these are the simulation results we would like to present in this presentation. To conclude our presentation, we would like to thank Dr. Bass, who provided generous help for us and made this project possible, as well as our lab peers for their generous support. Thank you very much. And here are the references we cited in our presentation. And thank you very much for your attention.